Yeah.
So Mrinal, the second one is Victor.
All right. So yeah. So do you remember where we were? So we were here. So we had a linear system. So each of the EIs gives us a linear system in the P and the Q. And what we want to show now is that we can actually solve this linear system in the sense that there's a unique solution to the system. We know there is a solution because f equals g times h, and that gives you a solution. But we'll show that there's a unique solution. In particular, the solution will precisely require the higher degree homogeneous components of g and h. So the coefficients are, so the matrix is a matrix of polynomials at the moment. We'll reduce it to a matrix of constants. Okay, so let's write this linear system somewhat carefully and then observe some things about it. Somebody asked in the break that, so I made a fuss about the GCD of G and H being 1 initially. I haven't used that fact yet. So somewhere it has to be used. It will be used in the next 10 minutes. Okay, questions about where we are, what's left? Right, exactly. So we know that G gives a solution to this system, and we'll now show that there's a unique solution. Right, exactly. So we'll show that there's a unique solution, which means that whatever solution we get must come from the G and H. Okay, so let's just write that linear system in a way that is more identifiable. So we have a matrix times a vector equals another vector. So we know what this vector is. This is maybe with a minus sign. So E0 of AB, E1 of AB, E sub D minus 1. So this is that vector. This vector is P0 up to Pk minus 1, Q0 up to Qr minus 1. Then we have the matrix. So each of the rows of the matrix is indexed by an E. So there's an E0, there's an E1, and so on. E sub D minus. Okay, so let's just try to write a few entries of the matrix and see if this looks familiar. What I want to conclude is that this matrix is full rank. Okay, so there's something that I should say here while we are at it. So note that we are looking for P's and Q's which are homogeneous polynomials of degree L plus degree L. That was the setup. Now, the only way a term like this, some P sub j times some other polynomial contributes a monomial of degree at most L, is that you are looking at the constant terms of the coefficients. Right? That's the only way this can really contribute a degree L monomial. So when we went mod x to the L plus 1, I could have really looked at the coefficients in this sense. So I'm only interested in the constant terms of these coefficients. Right? So each of these coefficients is a polynomial in x. But this P is already a polynomial of degree exactly L, and we are going mod x to the L plus 1. So the only non-zero contribution mod this ideal are going to come from terms where you are looking at the constant terms of the coefficient times the polynomial P and the polynomial K. So okay, so that's what, so that really addresses Srikanth's comment that the matrix we were getting initially was a matrix of polynomials in X's, but the only interesting part of it for solving this problem here is the mod X part of it. So you just look at the constant term of all the entries and look at that matrix, and if you can show that that matrix is full rank, we'll be good. Okay, so now let's just write down what the matrix looks like. So the rows of this are indexed by EIs. The columns are going to be indexed by U0 up to UK minus 1, b0 up to vk minus 1, vr minus 1. And okay, so this entry here is going to be the derivative of E0 with respect to U0 evaluated at A0, B0 and so on. So the entry here is going to be the derivative of the row index with respect to the variable for the column index evaluated at the point A0, B0. Okay, now just to recall, these A's and B's, these were polynomials which agreed with the G's, GI's and HI's up to homogeneous components of some degree. Now A0 and B0 is really the degree 0 homogeneous component of the AI's and the BI's, and based on the hypothesis of the lemma, they are equal to the homogeneous component of the GI's and the HI's. So I can just write G0 and H0. So we have a matrix which looks like this. This gives a system, a linear system which looks like this, and we are interested in the solutions to this system. Okay, so I really need to draw a bigger matrix so that we can see some of the entries, and that will give us a good sense of what this is. Okay, so let's draw a giant matrix. Let's look at the first column. I wrote the EI's here. So if you look at the derivative of E0 with respect to U0, you're going to get minus V0. All the other U derivatives are going to be 0. Right, so there's a whole bunch of zeros here. Now if you look at the derivative with respect to V0, you're going to get minus U0. And then everything else will be 0 in this row. Okay, so now let's look at E1. If you look at E1, the derivative with respect to U0 is going to be minus V1. Then there's going to be minus V0 here, a whole bunch of zeros, and something very similar here. So minus U1, minus U0, whole bunch of zeros, and so on. So the next derivative is going to be minus V2, minus V3, and so on. And this is going to be minus V1, minus V2, and similarly here. So what's going to happen is that this is what it's going to look like. So we have the vector V1 up to V r minus 1, and we'll just shift it down like this, and you'll see a similar picture here. All the other entries are going to be 0. Okay? So this is the matrix. And then we are going to look at an evaluation of this matrix where the AI's and where the UI's and the VI's are going to be substituted by GI0 and HI0. Okay, does this matrix look familiar? This is the resultant. This is the resultant of what? This is the resultant of what? It's so it's the resultant of all right, so we are looking at this matrix, and we are going to do the substitution that U is going to be replaced by G0 and V is going to be replaced by H0. So this is really the resultant of G comma H with respect to Y. This is evaluated at the all zeros point. Okay? Okay, so now let's go back to the GCD condition that we had initially. We knew that G and H as univariate polynomials in Y had GCD 1. That implies that this resultant matrix, when you look at the formal resultant without the substitution, the resultant matrix is non-singular. Okay? Now it might happen that when you substitute the origin into the matrix, you get something that's rank deficient. Right? So I should have said this initially, that I'm going to do an initial random translation of the coordinate axis. And I'm going to assume without loss of generality that the resultant matrix, which as a polynomial matrix is non-singular, actually evaluates to a non-singular value at the origin. Otherwise, we could have just done the whole lifting by looking at ideals generated by xi minus alpha i's or something. Okay, so as a formal polynomial matrix, the resultant matrix of G and H is non-zero because their GCD was 1. And without loss of generality, we'll assume that this matrix is actually non-singular even if you evaluate it at the origin. Is this fine? Okay. All right, so that basically implies that this is a full rank matrix, which implies that this is a system we can solve. This is a full rank matrix, and note that this is a matrix over the underlying field. So all I need to do in order to get the PIs and QIs is take an appropriate weighted linear combination of the EIs that we had for the solution constructed so far. And you're looking at D cross D matrices, taking a weighted linear combination costs some D square or D cube additional wires. All right, so GCD of G and H viewed as univariate polynomials in Y was 1. This was our initial assumption. So this implies that if you look at the Sylvester matrix of G and H, this is a formal matrix. So this is full rank. And this implies that for a random alpha in f to the n, the evaluated matrix that you get by looking at G of alpha, H of alpha, is full rank. And all I'm assuming here is that alpha is the origin. If it's not, then we would have handled this initially. We can do the entire lifting centered around alpha as opposed to around. Okay? All right, so what this shows is that you can solve for PIs and QIs. So we already had circuits for A and B. There was a circuit CL-1 which gave you A and B. In order to look at EI of A comma B, you just put a copy of the circuit for EIs on top of the circuit CL-1. So let me draw a picture and maybe it will be clear. So our hypothesis for the lemma said that we have a multi-output circuit, C sub L minus 1, and the outputs of it would be A0 up to AK minus 1, B0 up to BR minus 1. In order to get circuits for the evaluation of EIs on these guys, I'll just put a copy of circuit for E0 up to E1, E0 up to ED minus 1 here, and I'll join the wires appropriately. This gives us access to this vector, and then I have to multiply this vector by the inverse of this matrix. So there's some wiring that's happening here. So this is at most D cube wires, and at the end of it we have access to basically a solution to. Right, there's a little bit of care to be taken here because you really, in order to get your hands on PIs and QIs, you really have to look at the solution that you get and then go mod to the L plus 1. But yeah, this can be taken care of. It's not an issue. So at the end of all of this, and so now what I'll do is, once I have access to PIs and QIs, I'll look at A0 plus P0 up to BR minus 1 plus QR minus 1, and this gives us our AI hats and BI hats. So this is what the lemma concludes at the end of it. And this whole circuit that we have here is C sub L, or C sub L plus 1. I'm not sure what notation I used. Okay, and the size of C sub L plus 1 is the size of C sub L plus whatever happens here. And note that not a lot happens here. This is some d to the 5 factor at most. Okay? All right, so questions? Yeah.
The P's that you get here need not be homogeneous degree as well.
Right, but you can argue that, exactly, you can argue that they don't have lower degree components. Their minimum degree component is degree L, and then there's some higher degree junk, but it doesn't matter. No, we can't pay for that extraction, really. We cannot pay for this extraction.
So we just add it to the initial A and B.
Right, exactly, right, and that works, yeah. Questions? Okay, so the whole point in this was that this matrix, this linear system that shows up here, corresponds to this matrix, which actually is full rank. And we didn't observe it for a while. This was just an accident, and then it gives a proof. Okay, so yeah, I guess we could have avoided taking a break and then taken a longer break. Okay, so let's spend a few minutes trying to understand why does this not give an algorithm. So why does this not give an algorithm? So let me summarize what really happened here. So the base case for this iterative lemma that I had written here was the case when you're looking at factorization mod x. So you have gi's and hi's mod x, which is really their constant term. And everything we did in the proof of the lemma is actually constructive. We could have done this algorithmically. So if somebody gave us this degree 0 components of the gi's and hi's subject to the condition that this matrix is non-zero, is non-singular at the origin, then we could have done everything algorithmically. This would have given us an algorithm. So the issue is that we don't have access to the degree 0 components of the gi's and hi's. And one way of trying to get access to the degree 0 component of gi's and hi's is to look at the polynomial f that we had initially and just go mod x. So set all the x variables to 0, so you get a univariate polynomial in y. Factorize it by univariate factorization algorithms. So potentially over complex numbers, you get d roots. So your f completely factorizes as product over I, y minus alpha I. Now some of these alpha i's will come from G, and some of these alpha i's are coming from H. But the point is that we don't know which one comes from where. But what this argument roughly says is that if you told me correctly which one came from where, then everything else, we can reconstruct the full factors at the end of the process. Okay, questions? Yeah. No, you need the uniqueness, yeah. You need the uniqueness. If there were multiple solutions to it, you will have to somehow argue that all the solutions have a small circuit complexity or something like that. That seems a bit too strong. Yeah. No, but you don't know that that solution has a small circuit. You know some solution has a small circuit, but. Questions? Okay. Right. Okay. I don't have to say anything else. Right, yeah. Right, you prepone my talk by 24.5 hours. I can prepone the break by 20 minutes and it doesn't.
So here the point is that if you wanted to do this for branching program,
Yeah.
So one of the,
Yeah.
it seems inevitable that you can somehow argue all of this just as additive blow up.
Yeah. So it seems that you have multiplicative blow up. Basically, one of the issues is this. So in a branching program, this is some composition happening here, right? Now, given a branching program for E, if you want to, and you have branching programs for A's and B's, if you want to look at the branching program for E of A comma B, you somehow have to go to each of the variables, AI's, each of the UI's and VI's which appeared here and plug in a branching program for AI and BI there. So that's multiplicative blow up. And that seems too expensive. Here it was just additive. You just
When the process stops, you would have computed a polynomial that agrees with G
Yeah.
up to terms of degree.
Yeah.
But it has a bunch of higher order.
Right. So there is a final homogenization that has to happen at the end of it.
degree could in fact be exponentially large.
Oh yeah, degree could double every time. We are doing compositions which will probably increase the degree quite a bit.
What's the idea for this? Just replace each gate by the
No, just
degree D.
right, exactly. So every day, right, throw away the higher degree components. So you can't really do interpolation here, I think, but you can do homogenization using Strasson's. Okay. Oh, I don't know if it works anywhere apart from circuits. Like branching programs, I don't know. I did hope at some point this would work for branching programs. The reason being that there's some linear algebra happening, and this seemed like tailor-made for branching programs. Like I don't know anything about non-commutative factorization, like on the spot. Yeah. No, there will be some, you have to do D iterations, right? So there's some D, there's multiplicative blow up by D. Yeah, yeah, there's some final homogenization. It really seems to use the fact that we have a circuit where we can reuse computation, output multiple things at once, and compose without paying, with paying just an additive cost at every point. Yeah. No, we don't know how to do root finding with ABPs either. There are upper bounds, there are non-trivial upper bounds, but Cheening might talk about some of this. But yeah, we don't know how to do it in polys. In fact, for many of the applications, for the applications I was initially interested in, root finding would be sufficient.
One of the things that you get usually is that if you have a solution mod, an ideal you get a solution mod
I square, yeah.
So somehow the growth is larger.
Right, it's a quadratic convergence. So.
Didn't evaluate it at 0, then wouldn't I be getting?
Yeah, so you'd be inverting a matrix with polynomial entries then. So it's not super clear. I'm sure that it can be done, I think, but I'm not very sure what's going on. Yeah. Yeah. The question was, what are you trying to optimize in the process? But
no. So I mean, one thing that seems completely hopeless for branching programs is that if your degree ends up being exponential.
Yes.
And you're trying to get a low degree component.
That's correct. Yeah, you can't. Yeah.
But there are other issues.
No, for branching programs you can do that, right? Why the circuit thing will just work for branching programs. For anything else, it's not clear.
No, the branching program will always have low.
Right. It has small degree. Okay.